Welcome to Study Loop.
Okay, for this question, we want to figure out which of the D-Aldopentose structures that we could start with that when it converts to an aldaric acid, it would be optically inactive. But we want that same structure when it goes through Wohl's degradation and turns into D-Aldotetrose, we want that to become an optically active aldaric acid. So through process of elimination, we need to figure out of these structures which one would work. So we start with our structure. Notice that we have our pentose 1, 2, 3, 4, 5, and we have our OH on the right side satisfying the D part of the structure. So what are the options? The options are OH all on one side. We could alternate our OHs and it would look something like this. Or we could put both of our OHs on the left side and we would have a structure that looks like this. These are only the options when it comes to D-Aldopentose. So when this goes through oxidation and turns into an aldaric acid, we get something that looks like this. Now we need to figure out which one of these are optically inactive. And we need to just do a quick review and remember what it means to be optically inactive. So inactive, we would need to have symmetry or be symmetrical. So the easiest way to figure that out is to just sort of draw a line through these structures and ask yourself, are they symmetrical on both sides? And you'll notice that this one is symmetrical. It is optically inactive. This structure, the same, optically inactive. When we look at this one, however, notice we have OH on the bottom, but we have H on the top. This one is not symmetrical. So this structure is optically active. All right, so this one's going to be out. This one is not going to be the structure we're starting with because it doesn't fit the criteria. It needs to be optically inactive. So we're down to these two structures. So we have to figure out of these two structures, which one, when it goes through Wohl's degradation, would give us a structure that would become an optically active aldaric acid. So let's look over here at our aldotetrose. So I've basically gone through Wohl's degradation. We've reduced this down from 5 to 4. 1, 2, 3, 4 carbons, and we've got our tetrose. So when this one goes through oxidation and we turn it into an aldaric acid, which one of these is going to be unsymmetrical or not symmetrical? So drawing a line through, notice that this one is symmetrical. If it's symmetrical, it is optically inactive, and that's not what we want. This one, however, is optically active because it is not symmetrical. So, moving backwards, this is the aldotetrose structure that would result in an optically active aldaric acid, which is then coming from this aldopentose structure that would give us an optically inactive aldaric acid.